Thank you. I, first of all, would like to thank the organizers for organizing the meeting and for inviting me. And today I will talk about Hawaii and other Pacific hotspots. This is a work done in collaboration with Al Hoffman and Connie Klaas. Now, the Hawaiian hotspot has a long-standing intraplate volcanism, and these are the volcanoes. The colors are different. Oh, God, no. Sorry. Anyway, never mind. Oh. It comes back. Never mind, let's stay with these colors. So these were the volcanoes formed in the last 4 million years, roughly. However, volcanism is much older and probably goes back to at least 80 million years. This is also the most vigorous hotspot on Earth, and the volcano lifetime is basically 1 million years. So today we have Loihi that is still underwater, that is growing. It's 0.2 times its lifetime. Kilauea is in a chill stage, and older Mauna Loa and Mauna Kea. These volcanoes are actually quite big because their volume is at least 60,000 cubic kilometers. They stick out of sea level at least 4 kilometers, and you also have to consider that down below the water you also have at least 5,000 meters. And the basal radius is quite large. So ever since the 70s, it was suggested that there was a mantle plume, since Morgan, but the question is, where is the Hawaiian mantle plume? And this is a question actually for seismologists. I show here only the most recent results, but several seismologists have been working on hunting for mantle plumes. This is Schmer a couple of years ago. Now the idea is to use SS precursors, so you have an S wave that is reflected at the surface, but also S waves that are reflected at the bottom of the 410 or at the bottom of the 660s. Now these SS waves will arrive before the waves reflected at the surface. So by calculating this delay time, you can calculate the thickness of the transition zone. And what they find around Hawaii, let's say this is Pacific, this is Hawaii, is the transition zone is actually thinned. And the zone where this transition zone is thinned is to the south. In another, it's cutting this is a resolution problem, right? This is cutting the upper part, never mind. Now, this is a recent work by Kao and collaborators. They use somewhat the same idea. You have a source, and the S waves are reflected at the 410, at the 660s, or at the surface, and they get to the receiver. So in a hot plume, if you consider the olivine phase transition, in a hot plume, you have a positive Clapeyron slope for the phase transition at 410. Therefore, you would expect a deeper 410. Therefore, the colors would be in the bluish. This is where they find the bluish color for a deeper 410, and also in this area far away from Hawaii. If you consider the phase transition at 660, it has a negative Clapeyron slope. Therefore, the transition is expected to be shallower at 660. We would go in the red colors. Again, in this area, you have red colors. In this area, you have blue colors. In this reasoning, then, you would have a thin transition zone and a negative correlation between the two deflections of the phase transitions. The only area, actually, where you can have a negative correlation is to the southeast of Hawaii. However, the authors do not consider that the plume conduit, or the Hawaiian plume, is situated to the southeast of the active volcanism, but they consider that there is a somewhat intriguing zone, 1,500 kilometers to the west of Hawaii in this area, and they suggest that the 660 phase transition is actually deeper because in a hot plume you do not observe the olivine phase transition, but you observe the majorite garnet into perovskite phase transition, which has a positive Clapeyron slope, therefore it would be deflected downwards. Now, with a positive Clapeyron slope, this phase transition wouldn't act as a barrier to convection. They suggest that actually maybe there is some ponding of a hot material, but and note that in this case, if really the source region of Hawaii is 1,500 kilometers far from the active volcanism, then we cannot use surface lava to understand something about the deep geochemical structure. Now, I would like to say that maybe there are some warnings. I'm not a seismologist, so I cannot comment on the quality of their data. However, as a fluid dynamicist, I would like to say that in this model, the dynamics is completely missing. They do not want to consider a plume conduit here because they claim the excess temperature would be too low, around 150 degrees only. However, at the end, they do not propose any conduit to feed the volcanism. Now, this is the strongest hotspot on Earth, and it is a bit surprising not to find or see any conduit. Now, there is another study also published in Science. This is S-wave tomography. The red colors correspond to slow S-wave velocity. This is the island of Hawaii. Here we look at 100 kilometers depth. You see an elongated region of slow velocity, elongated in the direction of plate motion. This is something similar to what is observed at 300 kilometers depth. And then when they look deeper into the lower mantle at 900 kilometers, they do find a zone of slow velocity anomalies to the southeast of Hawaii. Now, these studies have been somewhat confirmed also by P-wave velocity structure, a recent paper by Cecily Wolf. And in this case, you would tend to put a plume conduit somewhere here that is actually tilted by the motion of a plate. And from now on, we will somewhat stick with this model where there is a continuous conduit somewhat to the southeast of Hawaii that is feeding the plume. Now let's turn to geochemical observations. The geochemical observations have been known for a long time. The two volcanic chains, Kea and Loa, are geochemically distinct, even if they are not too far away, okay? And these differences are observed in all basically isotope ratios and particularly well in the lead space. So this is 206, 204, 208, 204. You see that at a given 206, 204, lower trend volcanoes systematically have higher 208, 204 with respect to Kea trend volcanoes. Now, it was suggested by Abu Shami's work in the Hoffman group that this would suggest a sort of bilateral zonation of a plume conduit. Basically, one side is somewhat red-colored. It would be probably Kea-type source with recycled lower crust or lithospheric mantle. The other side of a plume conduit would be some more blue and containing recycled crust and sediments. But the very absolutely fascinating thing, it was to discover a paper that I really liked and inspired my work by Huang et al. And they had the original idea to look at other hotspots with double volcanic chain. So not only Hawaii, but also Samoa and Marquesas. And what they find is that probably this bilateral zonation is not unique to Hawaii, but is something that we can find also in other double volcanic chain. Okay, so let's look in more detail at Samoa, for example. This is the Tonga Trench. The colors correspond to a bathymetric map, okay? These are the part of the islands that are immersed. Now, the active volcanism in Samoa is actually here. The plate is moving in this direction. And there is more active volcanism today, but it's not related here to the hotspot. And here you have two trends, the Vai trend and the Malu trend. And when Huang et al. Plot on a lead. We will come in a second to explain what it is with radiogenic lead isotope ratio versus epsilon neodymium. What they find is that systematically, at a given, for example, epsilon neodymium, the volcanic chain to the north, for example, Chaire trend in Hawaii, systematically has lower radiogenic lead isotope ratios with respect to the chain to the south. And this is true also for Samoa. Given epsilon neodymium, Y trend would have higher epsilon neodymium than the chain to the south. Now, let's define, we will use extensively this isotope ratio that we called radiogenic lead isotope ratio. This is how it is defined. Thank you, Manuel Moreira, for introducing all this before. The key point here is that this ratio actually represents a ratio of thorium, the parent elements, thorium and uranium, integrated over the Earth history. It thinks that it takes a long time to modify a little bit this ratio once you have a slight modification in uranium-thorium. Okay, so now that we have defined this, let's go to the second observations done by Wang et al. And here they plot now this radiogenic lead ratio over latitude. So this is Hawaii, fairly low values. You move to the south, Marquesas, higher values. More to the south, Samoa, even higher values. So we can ask the question now, what is the origin of these isotopic differences between parallel volcanic chains? And there are two opposing answers. One, and this is mainly the group by Gary Ito, and they suggest that is because of shallow sublithospheric melting processes. Other groups, and I include myself, consider that the causes are mainly related to large-scale heterogeneities in the deep mantle. Now let's have a look at this model, the shallow origin model. Now they conducted numerical models. So here you have a Hawaiian plume, and this is the lithosphere. The lithosphere, oceanic lithosphere for around Hawaii, is probably 90 million years old. And it is true that you can have processes of small-scale convection that would develop, and they find that this would somewhat erode the base of a lithosphere, forming a sort of washboard topography. And then the Apulian plume is actually, imagine, a mixture of peridotite and more fertile pyroxenite. And what they explain, they suggest, in order to explain the differences between Chaire and Loa trend, is that there is a thinner lithosphere, for example here, thinner lithosphere beneath the Chaire track, and this would cause a higher melt fraction and more sampling of isotopically depleted peridotite. Now, this idea can be tested geochemically, and this is what Al Hoffman did, is work in progress. The idea now to test this is to use lanthanum, which is highly incompatible. It is inversely proportional to the melt fraction, and another ratio, lanthanum over ytterbium, which is not significantly affected by fractional crystallization. Now let's consider that if we fix the melt fraction, then a pyroxenite-derived melt should have higher lanthanum over ytterbium than peridotite. So let's test Balmer model. In Balmer's model, for Chaire trend, you have a thin lithosphere. We said higher melt fraction, you would expect low lanthanum. More sampling of peridotite, you would expect low lanthanum over ytterbium. And for Chaire trend, this is exactly the opposite with respect to what you observe. And this is similarly true for lower track volcanoes. In their model, you would expect high lanthanum over ytterbium. What you observe for basically all these volcanoes, most recent volcanoes, is just the opposite. So I think that this model doesn't stand a geochemical test. So let's move to deep origin models. This was a recent paper by Dominique Weiss and co-authors, and they suggested that probably the difference between the lower and Chaire trend is due to the fact that lower part of a Hawaiian plume actually samples part of the low shear velocity zone that is located in the deep mantle. This is something that we have already seen during this meeting. This is a map by Rizema with shear velocity variations at 2,800 kilometer depth, and you can see that maybe indeed the lower part is actually sampling more of this large low velocity province. The large low velocity province has been associated already by Castillo, etc., probably correlated to geochemical provinces known as Duval anomalies. So it's not impossible to imagine that there is a link between seismic velocity differences or a large zone and maybe the Duval anomaly. So what we wanted to test was something very simple. Actually, my models are very simple, but we decided to start with something simple, understand it, and then move on and introduce more complexities. So my questions were, okay, now imagine that indeed in the deep mantle there is a large-scale gradient in, for example, these radiogenic lead isotope ratios, maybe a progressive increase from north to south. And the question is, how would this be sampled by a mantle plume? And if the deep structure in the deep mantle is indeed like this, can we explain the bilateral nature of a Hawaiian plume? Can we explain the variability in these lead isotope ratios observed in Hawaiian volcanoes? So this is our very simple model. This is a thermal boundary layer. This is the direction of the north. The red colors correspond to low Chaire-like values. As you move to the south, you increase the values of the radiogenic lead isotope ratios. Now, some of these questions have been somewhat addressed in even a more simple way, I would say, by previous studies, among which I would include lab experiments by Kerr and Meriot. They were injecting color fluids and eventually concluded that this is in case you have a sheared plume, like plate is moving in this direction, you would actually get a Hawaiian plume which is azimuthally zoned. And again, the colors here would represent geochemically distinct material. A few years ago, I did numerical models where, again, we were considering very simple thermal boundary layer structure, perfectly stratified, that would give a conduit structure which is concentric, and an azimuthally thermal boundary layer would give an azimuthal structure, absolutely in agreement with laboratory experiments. But here now, even if this case is so simple, it introduces some complexities, because now the geochemistry, if you want, is varying radially and also azimuthally. And so this is a view from above of a thermal boundary layer, and then we let the flow go. It's a very simple, purely thermal plume for now, and the conduit structure that we calculate has this shape. It's a completely new shape that has honestly never been observed before, and I think it has never been observed before simply because nobody before looked at this kind of geochemical pattern in the thermal boundary layer. So we found a novel zonation that we called lobate, because there are basically two concentric lobes, and you see that it's basically bilateral with important differences between the northern and the southern part. Now, in the next slides, I will show you how we can go from this sort of stripe in the thermal boundary layer into this zone in the conduit. Now, let's start with something very simple. Again, I'm sorry it's cut here. Let's look at the thermal boundary layer. This is the axis where the plume will be upwelling. We start with two bands of different colors, and the initial position is 200 kilometers from the axis. This one is 500 kilometers from the axis. Never mind, as convection starts, the plume is rising, is actually entering the conduit right in the north direction, which was the closest initially to the plume axis. This is the plume axis. We can keep track of a conduit structure. This is again the north direction. So this material would appear in the north-south direction, and as time goes on, the lobe actually increases in size, in radius, and in angular apertures, and the other band is actually flowing. There is some shear due to the velocity field, forms a cusp, and up it goes again. So eventually, we would have produced this lobate structure inside the conduit. Now, in order to understand better the geochemistry, imagine to put some tracers and to follow the trajectory. So we have 3 points, A, B, C, inside the conduit. Here they are. And there's the question, where do they come from? And when you trace back, this one has traveled with the highest velocities. Therefore, it comes from further north. Therefore, this tracer will actually carry the lowest value that are observed to the north, therefore deep red colors. So eventually you see that in the north-south direction you still have the highest gradients, but note that now most negative that were far away and most and highest, let's say, values that were further south are now close to the axis. We tested also different models with different initial distribution. The result is that it doesn't change much. You still get this lobate structure. Now geochemists will say, well, but what do we do with our red and blue? We really liked it. Yes, you can still use it, but you should know that your simple red and blue is the result of a very special case in which the difference here in the thermal boundary layer happened right where the plume axis is. This is the only case where you can have perfectly bilateral red and blue scenario. In all the other cases, we find again this lobate structure popping up again, and we think it is a robust result. Now let's move on and put it inside the Hawaiian plume. I don't give details of this model. It was published a couple of years ago. We have a strong, fully 3D plume sheared by the plate velocity. Everything is reasonable. And what we do here is to take our lobate plume conduit and use tracers to advect their geochemical fingerprint and ask the question, what happens once we are in the melting zone, okay? And first of all, you can see the yellow colors corresponds to temperature. And first of all, you will see already that we can find a bilateral zonation with the Ka into the more reddish part and lower into the highest values. Now I produce maps of this. And so this is again looking north. And this now would be a map of the Hawaiian melting zone. The plate is moving in this direction, and just to locate some volcanoes, this would be Loihi, this would be Mauna Loa, this would be Kilauea. First of all, we do see that we find a basically bilateral structure, and when we calculate the evolution during a lifetime of a volcano, we do find that the Loa Trend volcano systematically has, during all its lifetime, systematically has higher values than a Kea Trend volcano. So I think that first of all, we can explain the basic observation of a bilateral zonation and distinct volcanic chain between Loa and Kea Trend. You also see that with respect to an ideal central volcano that would be here, double volcanic chains can reveal this heterogeneous structure much better than a central volcanoes. So parallel volcanic chains can be really important to tell us something about the deep structure of a conduit and probably also the thermal boundary layer. We also see, well, in the other cases, which I call case B, the structure is slightly different, but again, we find the same basic differences between Loa and Kea Trend. Now we can ask the question, how do our simple predictions compare with observations? And again, our models are very simple. We didn't tune everything. 5 minutes, okay. First of all, we go, so given the distance with respect to the plate motion, we see that for a Loa Trend volcano, you have increasing values during the shield stage and then decreasing during the post-shield. So we took Dominique Weiss' paper. They have sampled the section of Mauna Loa underwater. So we have all the samples, and this is a very rough representation, but actually the values of the oldest part, submarine part of Mauna Loa, actually plot here. When we compare to Mauna Loa late shield, we do find that these values are actually lower, so our trend is somewhat first order satisfied. For Hualalai, somewhat similar, is less statistically significant, but shield in Hualalai, which is here, is actually slightly higher than the post shield. When we are looking at Chaire trend volcanoes, the best record is actually given by data from the Hawaiian Scientific Drilling Project, and which provides all this isotopic evolution of Mauna Kea over at least 600 kilo years. And when we plot this, the model age, with respect to our radiogenic lead ratio, we do see that as you go back in age, the values tend to increase. So when we roughly plot these values, are here. This is what we showed, but keep in mind there is a time evolution, and we do satisfy the idea that as we go back in time, older lavas should have higher values. When you compare Mauna Kea with respect to Mauna Kea post-shield, again, you see a decrease in these values, and again, we think that we satisfy our predictions. So basically, our model with a deep southward increase in lead isotopic ratios can, to first order, explain observed trend over long time scale. With my models, I can explain variation over long time scale, not variations between one lava flow and the other one. Okay? Now let's have some fun. We have seen that for Hawaii, we can put an increasing arrows, so higher values of lead somewhat to the south. The plate is moving in this direction. This is the case I just showed you. Now let's think about Galapagos. Let's have fun. Where would you put the arrow? Galapagos is here. Intuitively, if we look at this tomographic image, we would put an arrow where the enriched material is somewhat to the west. So let's do it. The enriched material is somewhat to the west. The Nazca plate now is moving in this direction. We can calculate the conduit structure. We can calculate using Hawaiian models, so it's a bit of an assumption, but let's go for it. And the distribution of lead that we would calculate in the melting zone of a Galapagos plume would have this shape, which is interestingly quite similar to this well-known horseshoe pattern that is observed in Galapagos with enriched material down here and depleted material to the west. Yes, no, to east, sorry. Now, I don't go into the details of this, but remember that this geochemical zonation of the Galapagos archipelago is not observed only today, but it goes back to 14 million years ago at least. So this is a zoned plume, and it has been zoned for many million years. And I do think that this is a signal of a deep mantle. It cannot be a shallow origin. Now let's have more fun and consider a society hotspot, and probably this hotspot that would be down here. I would put the gradient of increasing lead isotope ratios in this direction. Pacific plate is moving in this direction. So basically what we would predict now is a southern side that is has geochemically low values. And I think is actually in agreement with extremely recent values observations by Pine and Jackson, which looked at these double volcanic chains. There is probably more work to do also on other hotspots. I don't have time to continue on this, so I will get to my conclusions. The geochemical zonation observed at Hawaii, and I think also at other Pacific hotspots, reflects large-scale heterogeneities in the Deep Mantle, which is a source region of plumes. Now we model this large-scale increase in radiogenic lead isotope ratios in the mantle, and we have seen that even with this basic, very simple model, we can obtain, first of all, a low-bait zonation in the plume conduit, which is new, and second, most importantly, this distinct isotopic ratios between the Chaire and lower volcanoes. And we also predicted a different evolution between shield and post-shield, and this roughly fits observations of all 6 Big Island volcanoes. Thank you.